Okay, so in the previous lecture, we sort of understood how to sort of, or understood this, did a fixed effects model in R and tried to understand these 4 questions by a simple one-way element, right? So now I just want to just, we've done this last time. I just want to sort of reiterate how to go towards random effects. So let me write down here, random effects. So here, what we will do is, so let's just go back to the original model. So original model, what we do, we had this Yij. This Yij is the observations that we have for the jth observation. I'll call it in factor level I. Okay, so I'm using different words each time, but just to sort of give you an idea how people use it in various contexts. Sometimes use cell, sometimes use J. I just call it as a jth observation in a factor level I. Right. So now, so far, the previous RF exercise that we did, we modeled Yij as just as having a fixed mean mu plus a factor effect alpha I or a group of alpha I plus an error epsilon ij, where j was IID normal 0 and square, right? So just the j is equal to 1. Here I took a fixed thing, but I can do n sub I, and I'll take i's from 1 equal to 1 up to, let's say, some number, let's say capital I. And the crucial thing was we assumed that the randomness is only in this person. This is color. Let's call it color. So epsilon ij's were the normal with mean 0 and variance sigma squared. They were all independent. And the alpha I, which is the group effect or the factor effect, they were all fixed effects. That's what we mean. So alpha I was the fixed effect. So this is what typically is called as a one-way. What we did in the previous exercise was to treat that experiment that we did was a one-way ANOVA model. So now what we do now is we try to like we discussed last time, I could assume the alpha I also are random, right? So that's the random effect model. So let me go and write the random effect model down. So here in the next setup, what I'll do is I'll take the same thing, the Yij is the same thing, but like I discussed last time, in the random effects model, so let's call this a random effects model. So in the random effects model, what we'll do is we'll not only keep the alpha I epsilon ij is random, we'll also change the alpha I to be random. So what we'll do is we'll say alpha I also follows another distribution. I'll just call it normal with mean 0 and variance sigma squared. So now here I'll call it sigma square alpha, and here I have to do a different variance. I'll keep sigma squared. So sigma square alpha and sigma squared need not be the same. And they're all independent. So I'll assume independent effects on everybody else, and that's how I'll do this. So this is commonly referred to as a random effects model. So note by convention, that is the, so what I'll do is all the purple ones are random and the others are not fixed. So now we'll try and do it by R. We'll try and see how to the same data set. If I assume there's sort of a random effect in the brands, how will it affect the brand that randomly chosen? Then I have to sort of use that experiment. So now I'm going to introduce random effects and do the same model. For this, I will need a library called MER. One second, something wrong with my iPad. Very good. So I need a library called LME4. That's the one that implements the random effects linear model. So I'll do that. Okay. So let me call it'll load a package called matrix along with it. So let me call MO as the The way you call the random effects model, lmer, sodium versus tilde 1, 1 plus 1, and this is brand. For only data equal to. Let me call this M. So make sure that's the case. Or M0. Okay. So that let's try and do that. Let's try and do that into library and let's try and MO. So MO is done. So it'll take some time. It'll do the whole thing. Right? So now let's try and do a summary of random. What does it tell you? It tells you the following. So it tells you that it's a linear effect model by the random effects model method. It takes sodium and then the data frame is DF and the criteria convergence. It has a certain convergence. We'll do that later on. The residuals have this sort of variance in this sense. And the random effects of what? The variance is so much. The standard deviation is 4.6 and the residual is 0.8467. Right? So this is the variance. The residual is 0.7. That is the 0.716 is the sigma squared's error estimate. And the 21.74 is sigma squared alpha's estimate, right? And this 17.69 is the effect of the estimate of the mu. That's what we have found in this random. So this tells you so far that the estimate of mu was equal to 17.629. That's what it tells you, and it tells you the estimate of sigma squared hat next to sigma squared is going to be, that is the residue. The errors one is very, very small. It's 0.716, right? 716, very good. And the estimate of the alpha one, that is, I'll just call it sigma slash alpha squared, is going to be, what is it going to be? 20. It's quite high. It's 21 point. So there's a lot of variance in the brand. 21.274, right? 7. Very good. That's what I find it is. So now I'd like to go and find the deviation of average content by the brand, right? So let's do next step. So this command will tell you, if you do the random effects, that is this particular column here, it'll tell you the intercept in each brand. So let's see, this is the deviation. So let me just go to this. So what I want to do here is the following. So I want to go and find the deviation from the average sodium content, not overall, but by brand. Brand is what? So let's just do this. Then you do random effects. So this is M0, it'll tell you the exact. So it gives you the conditional variances for each brand. So the first one is 5.7, blah, blah, 7. So then I can go and do the same thing. I can apply the mean as well, the average. I do around and do the mean. The mean comes out to be, each thing comes to 6, 6.9, 6.9, and so on. Very cool. So let me now go to my notes now. I'll come back into the next part. Let me go to my notes now and let's try and discuss what this REML method actually is doing in R and where does it come to in some sense. So in the example, we found that in the example that we did just now, we found that in R, so in R, we used the library lme4. That's what we used, and then there we said that, and we applied the lmer function. So we applied the lmer function, and let me write this for lme4. And applied lmer function to understand, to estimate. And we found out various things. We found out that the estimate for mu hat was 17.629. The estimate for sigma hat squared was going to be 0.716. And the estimate for sigma hat alpha squared, we found it to be quite high, 21.274. Very good. So now I just want to sort of tell you what it used the REML command as the random effects model. So let's see, let me just discuss a little bit about what the model is doing. So the REML is sort of the ML refers to this sort of like a maximum likelihood. So this refers to what's called the restricted maximum likelihood. This I won't discuss in this course, but you can sort of look it up in some reference. I'll provide references for you in the notes. And we often say the predicted random effects and estimate fixed effects and variance parameters. So that's obviously. So we say what we do is we predict. So what are the things we predict? We predict random effects and estimate the. So we predict random effects. So write down, we predict the random effects. And we estimate fixed effects and variance parameters. This is something we estimate. Fixed effects and variance parameters. This is what people typically use. If you're using the fixed model, you say, I'm estimating the fixed effects and variance parameters. In the random case, you predict the random effect. So that means you're predicting a relational random variable and you're estimating a parameter random variable. That's what these two things mean. So let me write this down in different colors so it's kind of clear. So in the random effects case, you predict. In this case, you estimate. So in one situation, you're producing a relational random variable. In the other one, you're. So the model parameters are known on the random effect model are what? Mu, sigma squared alpha, and sigma squared. That's three parameters there. We do not consider alpha I as a model parameter, right? It's just a random relation from the model that you assumed it to be normal. So parameters here are these guys. Right? Let's write this down. This is a parameter. We call this an orange, and this is also a parameter. So these are parameters we're trying to estimate. So let's write down the parameters are. You try to estimate are mu hat, mu sigma squared, and sigma squared alpha. So hence this particular model has less parameters when there are large number of brands. So if capital I is very, very large, that's okay. It doesn't really matter. I'm not estimating all the alpha i's. I'm only estimating one sigma squared alpha. So this model has a random effects model has an advantage if I is very, very large. So with very few replicates. If Ni is very few, the random effects model is in place. This is fine. So let's write the usage of this model. Let's write down the usage of the random effects model is fixed model. So when is it useful? It's useful when you have the model has less parameters. The model has less parameters. The next thing is it's preferred. When is it preferred? It's preferred when the factors are large. That is when the number of brands is large. That is I is large. That is I is large. I is very large. And the number of repeats is low. Repeated measurements is low. So the number of repeats is low. The number of repetitions is small. That is Ni is small. In this case, you would there are a larger number of model parameters alpha I with insufficient replicates to estimate alpha I. So that means you don't do fixed effects, you do random effects. So that is if number of alpha I is large and number of Ni is small, then there's insufficient data to estimate alpha. So is insufficient data to estimate alpha. That's when you'll use a random effects model. So now I'd like to sort of just a brief testing hypothesis let's try and do, and then we'll in the next lecture, and then we'll come back and close this thing.